Okay, so this video is basically on the calculator path measurement problem. So basically, you're gonna understand that say I have a calculator here, this calculator here, this is a science calculator, but it can also easily, if it's encoded to choose the completion form of the coding system. So the coding system for tuition language is a calculator, and the calculator knows how the inputs map. So it knows how the input is called a codec. So it just knows the answer to the problem before it solves the question. You can try and go syntax error here on the calculator. So it's a we could calculator. So for example, if I have 3 plus 3, 6. But 6 is a number. Now I didn't ask for 14.1.1, but if I have 3 plus 6, it already knows the answer before it gives it to me. So it's usually interpretation mechanic. So the calculator obviously the problem is the input. There's the input form. Basically, if you want a program to really work for you as a codec, now you just have an input. All the inputs. So all the inputs are really encoded in the system. So it really knows what to take into consideration. So it really knows how to put it in. That's what it says. The calculator problem is this is a calculator here, this system here. But if it's a symbolic interpreter, it really has the symbols built in the calculator, so it really knows how to what the answer is ahead of time, or in any way of trying to find the input. So this calculator problem. So the calculator, the radical. So for example, you go to the wheel. So you also got the sleeping problem. So half sleeping problem. So if for example, you go to superposition problem. So if I'm half asleep, I'm half awake. If I'm asleep, I'm awake. If I'm asleep, I'm half dead. But if I'm half asleep, I'm half awake. So this is superposition. So half asleep and half awake are superpositions that the computer must simply. But if I replace sleep with off, if I'm half off, I'm half on. So if I go to turn my computer on, I'm turning my computer off too. So the goal is to use my computer is in superposition. So riff lang has a superposition state. So basically, the riff memory either half a memory allocated to sleeping, half a memory allocated to being awake. So this is put in a called superposition state. So it's a half state of sleep and awake. Because this is a bipartite state. So the engine is bipartite. So that's what so I'm saying an engine is bipartite. So that's how this works. This fails. So if you go to keep quick, we're not on. And it's off, it's in superposition. So until the superposition collapses into a different state, it will not resolve. So that's why that's why Rift has a deferred computing model. So it's either you have to sleep how it is deferred computing, and that's refers to a progressive DAG of half a week, due to bypass system. So you got a Rift token type, token to memory. Truth token type and token value, and the result is kind of a bypass sleeping problem. If I'm how human being don't put a human being on. You stimulate a human being, you stimulate a human being, stimulant. You arouse a human being's sense of sensory. So you stimulate a human being, stimulant, stimulus, stimulant, and stimulus. You stimulate the human being with a stimulant, given this stimulus. So that's what I'm saying. That's a half computing problem. So the half problem has a quarter problem. So you have a half, a quarter, which is 1/8 anticipation. It's the same going to be in a quarter. Take remember. So if I have 2 reads and 1 full writes per operation, and 2 reads and 4 writes, I'm most writing. So that half of both 2 reads 4 writes would be 2 divided by 2 is one half. Then you get about half read and right. This is 4. So I'm practicing. So I start with 4 writes and 2 reads. This is a right. This is a right flag. So the right flag is defined as 2 reads of 4 writes, and 2 reads of a sentence equals 4 writes. So again, 2 reads then 4 writes. 2 reads then 4 writes. Over system of bytes. Sequence of bytes. And you're gonna have half of that, which would be half of that would be 1 divided by 2. 1 half. 2, 1 half 4 would be 1 half, and this is called a half spin. So so you're gonna have 2 divided by 2. Or 1 half times 2. 0.5 times 2, which would be 1. 1 half times 2 would be 1. This is 1. So 1 byte of allocated to this. One byte of memory. 1 read. So you get 1 whole segment of memory to read to read only. So 1 half times 2 is 1 divided by 2. So this instead of 1 divided by 2, you get 1 divided by 2, which is 0.5. So 0.5 times 2 times 2. which equals to one whole, so you get half of a memory, so you get one whole single memory for reading only, and you get one half, one divided by 2, 0.5 times 4, which give you 2. So you get 1 divided by 2, you get 1 half. See, the 1 half is stored in the matrix, and we get half of it. You now get a quarter. So you get the ratio of 1 over 2, 1 divided by 2 for read and write. So 1 read, 2 writes, 1 reads, 2 writes. So this is going to half a read and write operation. This is what I call a measurement. So you don't take the measurement of a system computationally, Namdi. So you now have 1 divided by 4. 0.3. Now, 0.3 is the local anticipation. So if I'm anticipating something, I'm not doing a half, 0.4 times, like, this is times 2. And that's 0.5. Now, 0.5 is a quarter of a measurement, so half of a half. So you get half of a half. Then again, a 1 quarter, 1 divided by 4 times 1 divided by 4 times 4, which is 1. So you get 0.5 over 1 for read operation. So that's the same. So the superposition, if you got entanglement, superposition, and interference. So you don't want any filtration system. You want superposition. When you want to be deferred by need. So you got deferred by superposition, deferred by entanglement, and you have the inverse one, which is like -1, the third of interference. There's no interference in the system, so you don't want to defer any interference policy in the framework of open access format. So you don't want interference in the system in any shape or form, So interference would be something that's being hacked. So you want to take a measurement of the system to make this new interference. But usually collapse the state. So you want to so it's like, thank you guys for watching the video. Let's just go 5. The date is now 13:45. Time is now 13:45, 1:45. Time this is now 2:03, 2 second of the 3rd of 2006. Thank you for watching.